Today we'll be talking about real floating types. In our computer memory, we have a fixed amount of memory, but real floating numbers, as mathematics define them, cannot be stored in a computer memory because a real floating number may have an infinite number of digits. We have pi, which have an infinite number of digits. Or how can we store pi? In our computer memory, we work with floating numbers, meaning the decimal point can have different positions. That is, it is not fixed. All these are mathematical correct representation of 3.14. Depending on the representation we want, we can either represent it as 304 times 10 to the negative 1 or 3.14 times 10 to negative 1. Alright, a floating point number is composed of three parts. So we have the sign, we have the significant, which is also referred to as the mantissa. This exponent part can be omitted. According to the system that we have two types of floating types. Under the real floating type, we have three types here, which are float and long double. A float is a subset of double, which a double is a subset of long double. The system that does not enforce a particular way to represent floating numbers. This is defined by the implementation. For us to understand the limits which are found under the header file float.h, we are going to talk about the representation, how floating point is being represented. To define a floating type, we simply use the keyword float. We assign it a value, for example, let's say 3 point. Alright, so for us to print this number, we have different specifiers we can use in the printf function. For the print, we use the percentage %f, and we print our var name. Alright, so you notice that when we print percentage %f, we have 3.4 and we have extra 0. Then when we print with the percentage %e, this e is for scientific notation. The percentage %j will choose to represent the number depending on the number. Either it's going to choose to represent it as percentage %f or percentage %e. Each time you're printing a floating point using percentage %j, it will choose any of these depending on the length of the floating point number you want to print. We have another way to print our floating point using the percentage %a. The percentage %a is going to print your floating point in scientific hexadecimal notation. Run your program and see the output. So this is your value in a scientific notation. So let us talk about representing our floating point using a scientific notation. So -3, and we can print it as an output. We represent another percentage in front of it so that it should be printable on our command line. Floating points that are too big to be represented are considered infinite. So these are numbers which are like really small to be represented in our computer. So these are referred to as infinite number. The way we print double is the same way we print float, but this is a long double. The data type here is a long double, and we are printing it as a float. So we note that, maybe we can look at the console output. We notice that the precision is not accurate. Okay, so for us to have a more accurate precision, we can add L. Without the L, it is a double, and with the L, it is a long double. You can see that these values are actually identical. Meanwhile, in our code, we have defined a double here, and we have defined a long double with this constant literal here. Okay, and we print it using a precision of 30 digits. When we run our program, in Microsoft, we have the same results. But if we go under our GCC compiler and we compile our code using this compiling flag here, we run the code, we can see that it's different. Yeah, because we both know a long double have greater precision than a double. So with a long double, we have 18 digits of accurate precision. Meanwhile, with a double, I think we have 15. So there is a difference of 3. You will notice that the function from Microsoft runtime, which doesn't support 80-bit floating point, long double is equivalent to double under Microsoft. Alright, so that's just what I wanted to mention. Alright, so for simplicity, let us assume that our computer, we have a 12-bit register. That is, 8 bits is for the integer part and 4 bits is for the fractional part, and we are assuming that this is a fixed point binary fraction. Okay, so how can we represent the number 72.75, which is straightforward? We have to convert this 72 in binary, and to convert 72 in binary, we are using the 2's complement. That is, the most significant bit is the most significant bit have the negative sign. All right, so to represent the number, we have 1 here, 0 0. Since this is a positive number, we have 0 there, 0, and we also have 1 here, 0 0 0. Now the decimal points, how do we represent that in binary? We have 1 1 and 0 0. To represent 107.65.625 in binary will become 0 1 1. How am I doing this? I'm just adding this number. If I add this number, it's going to give me 107. All right, then in the decimal point, the decimal side of it, we have 1 0 1 and we have 0. This is our 107.625 in base 10 will be represented in binary using our fixed point binary fractions. Okay, even a 4-bit register with 1 bit before and 3 bits after the binary point, that means, and we are using 2's complement, that means that is the most significant bit is the negative bit, right? Now the largest positive number that can be represented using this register, this is the largest positive number. Okay, now we put 0 1 1 1, and if we sum this up, it's going to give us 0.875, which is the largest positive number. All right, now the smallest positive number not including 0, the smallest positive number not including 0 is 0. That is smallest. This is what the next one is, the smallest negative number. Okay, the smallest negative number, because we have 1 at the negative bits here, so the smallest negative number. Okay, this is the largest negative number. Alright, so let us talk about range versus precision. Now, precision relates to the number of bits used to represent a binary value. The number 0.5 in base 10, right, can be represented using 2 bits. That is 0.1 in base 2. Okay, now, but the number 0.1 in base 10, it cannot be represented. Alright, simply because we have a finite memory, and this pattern keeps repeating itself. We have 0011, 0011, 0011 recurring, so this cannot be represented in binary in base 2 accurately. Therefore, precision and accuracy are closely related. This simply means with low precision means less accuracy, even with binary fraction that requires a finite amount of bits. Precision is governed by the number of bits allocated to the mantissa, while range reflects to the exponent. So we have to know one thing. Where's my pen? For example, let's assume that we are having a floating point register with 8 bits, that is 4 bit for mantissa and 4 bit for exponent. Now, using the 2's complement, this is the largest mantissa. Alright, because remember here we are using 2's complement, so this will be like a negative value here. So this is the largest mantissa and this is the largest exponent that can be represented using this setting. Okay, so with this setting, right, with 4-bit mantissa, right, the binary point can move 7 places to the right, simply because we have to raise to the power 7 minus 1, which is equals to 7. So with this binary place, this mantissa can move 7 points to the right, and if this happens, that simply means it's going to be 0 1 2 3 1 2 3 4 5 6 7. So that simply means this is the largest positive value that can be represented using this setting, and this here will be the smallest positive mantissa. Now, why is it the smallest positive mantissa? Because Here, remember we have a negative, so this is the smallest on the exponent, and this is the smallest on the mantissa side here. This is the mantissa, and this is the exponent, right? So this is the smallest value. So with this is the smallest mantissa, okay, that can be represented. What does this simply mean? This simply means the floating point can move 8 places to the left, right? Simply because this is 2 raised to the power 3, right? Which is equals to, we have a negative here, which is equals to -8. If we move this mantissa, the smallest mantissa value, which is equivalent to 0.000488281. Now this is the smallest value that can be represented using this setting, and this is the largest value that can be represented simply based on the exponent here. Okay, if you look at the exponent, the positive exponent here is, this is 2 raised to the power 7 minus 1. Between, that is the largest and the smallest positive value that can be represented in our 4-bit register, there is a lot of gap. For instance, within this, we both know that the largest value to be represented using is 112, and the smallest is this, right? But using this setting, we cannot represent 7.5. We cannot represent 7.5 using this register, simply because of what? Simply because of we don't have enough bits in the mantissa. Alright, so we are going to suffer from precision loss. We change a little bit the setting, and we use 5 bits for mantissa and 3 bits for exponent. With this setting, we notice that this is the largest positive, that is 7.5, simply because if you take the mantissa and remove it 3 points, it's supposed to be 5 bits here, 5 bits here. And if you move it 3 points to the right, because of this exponent that is equals to 2, right? So we have 7.5, which is the largest positive number, okay? And if which simply means we should move this 4 times, which is gonna be like 100. So this is the smallest positive value. So I hope this really makes sense. All right, now for a given size of a register, the number of value that can be represented is limited. So this simply means greater position comes at the expense of range, right? Greater range comes at the expense of precision. There will be values that can't be represented accurately in binary notation. So let us wrap up this section by talking about normalization.